bear with me and I get this set up. I grabbed the wrong laptop when I left my house in a hurry this morning, so I'm going to be recording this on a laptop that's older than my second grader, but still has a functional USB port, so I think we'll still be able to make this work. It does have some problems with the keyboard, so please ignore any typos on the YouTube description and video, because there's nothing I can do about the fact that the U only works about a third of the time. Well, I could buy a new laptop, but I have one of those. I just not looking. All right, so let me get this going, pulled up. While that's going on, I have everybody's quizzes, your element quizzes. They went just fine. Everybody was worried, but you know, you do get to drop a quiz, so maybe this is the quiz you drop if you're really concerned about it. You know what? I'm not gonna. Is everybody okay if I pass these around? Is anybody worried about their grade or people seeing it? And I'll just do it at break. Let's just do it at break. We already went through the right answers, so there's no need for you guys to see it right away. I will make you wait a little bit longer on that. All right, let's talk. We're going to talk about. This is not the right version. Shoot, I didn't close the one on my desktop. We are going to pass it around. You guys can go through these. Get the right version of these. They're roughly off the order, except for a mark and Tiana, you're at the very end.
Yeah. There it is. It's so nice out there. Yes. And I think he did was that haven't done I almost lost it.
So our
For the 4 and 5. Yeah, I think 5. I don't know if the 5 is true, but for the middle one, yeah.
Oh, you're not sitting there? Let's go.
Yeah, like yeah.
Damn it.
Oh, this one, sorry. And then to figure out.
I wrote the exact same answer. I got it
Over here, I think we use that one. Yeah.
I have one of those.
Dude, I'll fight. Damn, I am not proud. We gotta make a decision.
All right, so a couple of common mistakes about these.
Yeah, hit me. I know
You guys didn't make your L look enough like an L and not like an I sometimes. So if I couldn't tell if you were writing CL or CI, then you got minus half a point. I graded the top half a little bit more strictly than I normally would when it comes to partial credit, because I'm just grading on two letters. Sorry, I'm out of breath because I ran back. All right. Other common mistakes on that were a lot of people invented new elements. It happens, it's to be expected. If you were anywhere close, I tried to at least give you half credit on the writing the names at the bottom part. But like I said, I was a little bit strict at the top. And now you know how I grade easy questions like this. where there's room for me to give you the benefit of the doubt, I give partial credit. With something as simple as a 2-letter abbreviation, you got a little bit less room for error. All right. There we go. Now we're talking about the right stuff. And I don't have the slides posted yet for today, but it's mostly going to be finishing stuff that we did from last week. Talking about periodic trends today. So if you have last week's slides, then you should be good to go. And I'll get these ones posted after class. Got a question about gamma rays. What is a gamma ray? How destructive could they be? Gamma rays is basically just really high energy light. I believe, I don't remember off the top of my head, but I think it's higher energy photons than X-rays.
Yes.
And thank you. And basically we can't see it. Once you get above a certain level, then the light has enough energy to knock electrons off of the molecules in your cells. When it does that, you get unpaired electrons that are called free radicals. And free radicals basically will go around and steal an electron from something else, but in the doing so, they make another free radical. So you get this chain reaction happening that winds up causing, and if it happens to react with your DNA, you get mutations occurring. And 9 out of 10 mutations don't have any effect. They're what are called silent mutations. They don't have any effect. Either the cells don't transcribe those genes all that often, or it's just in a section that doesn't really make a difference as far as what the proteins look like. But of those 1 out of 10 that do have a mutation that's noticeable, most of those just cause some form of cancer. So mutations are generally a bad thing, and high energy light is generally a bad thing for that reason. And anything that has free radicals in it should probably be avoided as much as possible. Although your body does have ways of dealing with that. And the #1 carcinogen in the world is oxygen. And there's nothing we can do about oxygen other than stop breathing. So you can never avoid all carcinogens when it comes to stuff like free radicals or light. So there's always a balancing act, quality of life versus minimizing risk, just like with anything else. But with free radicals, especially in carcinogens, you want to avoid the bad ones, but don't go overboard on it. Don't spend all of your waking hours worrying about what you're eating or whether or not your water bottle is BPA free or stuff like that, because you'll just drive yourself crazy and the people around you. Somebody asked about colors emitted by elements. Are they subjective because people would see colors differently? I mean, that's a tricky one to answer because it gets a little bit into cognition and perception and how the brain works, and we don't understand that fully. But at its most basic level, everybody's cones in your eyes react pretty much the same way to different wavelengths of light. They generate the same types of signals. They change shapes the same way. They send the same signals to the brain. Now, what the brain does when it gets those signals, we're still a little bit shaky on that. But in theory, everybody should see light the same way. What appears red to me should also always appear red to everyone else because we're looking at the same wavelength of light. Whether the subjective experience of red is the same for me versus someone else, that's more of a philosophy question. For me versus someone else, that's more of a philosophy question. And whether or not and other hallucinogens can change the way your brain is wired a little bit. And they're still doing research on that because cognition is tricky and we still don't fully understand it. But it's only going to be affecting your brain, not really your reproductive system. So it's unlikely to be something that you could pass on to your children, no matter how many psychedelics you do. Right? Because until it gets to affecting your reproductive system, it's not passed on to the next generation. So you could wind up with your culture being influenced by it. The way you raise your kids could be affected by, how much acid you've done in your life. But your kids' genetics are not going to be affected by that. Unless you start dosing your kids, and now we're away from genetics and just into child abuse. So it's unlikely because any environmental toxins, drugs, experiences are not going to affect offspring, generally speaking.
Okay, but
hear me out.
Okay.
Yes, let's go.
We learned how to use fire and incorporate that. If we learned how to use, like, I don't know, like magic mushrooms to give us like the ability to like, whatever. Incorporating that into a lifestyle, does that not change like a population?
So it can change the culture and society. Go ahead,
I
Mark.
was gonna say, like, anthropologically speaking, yeah.
Yes.
It probably had a huge influence on culture and
Yes.
like the symbolism and all that, but biologically,
Genetically.
you know, it's hard to change things genetically over very short time.
So here's where it could indirectly affect genetically, is if something about doing magic mushrooms gives you enough of an evolutionary advantage that you are significantly more likely to reproduce because you did shrooms than the people around you that didn't.
That would take like so long too.
It would be generation after generation after generation, and it wouldn't be directly, it would be because what you're really selecting for are the traits that lead to somebody wanting to take magic mushrooms. So being adventurous, being open to eating random mushrooms you find in the forest, those traits get selected for, not necessarily anything that's affected by the magic mushrooms themselves. So it could and definitely could affect how society forms and how technology is used and things like that, but not necessarily the genetics, which is where we kind of separate from anthropology from biochemistry.
Are we talking about just like psychedelics? Because I do know, like, if you have somebody who does like, I don't know, like a whole bunch of like coke or heroin and stuff, like their offspring is almost immediately affected. That's an actual physical thing.
But it's not a genetic thing, that would be a
okay.
developmental thing.
Right, so
Okay.
while they're a fetus.
Oh, okay, gotcha. Sorry.
So there's a separate class. I see you, Tiana, here, going to you next.
It's like it can change your brain chemistry, but you're not gonna pass it on genetically.
Correct. There's a separate class of toxins.
Mhm.
So there's carcinogens cause cancer, right? There's a whole separate class of carcinogens called teratogens,
Okay.
that cause mutations in your reproductive system specifically. Those are chemicals that could actually affect your offspring's genetics.
Is it one of those mustard gas?
I'd have to double check that. But yeah, they keep a list. The state of California has a list of things these are known teratogens, these are known carcinogens.
Is that like when you find a label on something that's like, this could cause reproductive hormones?
Bingo. Yeah. Most of those are teratogens, or they would render you sterile. One or the other. I think, frankly, the ones that render you sterile are probably more common than the ones that cause mutations in your offspring. But yeah, it's a whole different field, and it is. There are ways to directly affect the genetics of your offspring, but none of them good at this point. Tiana?
Isn't there
I'll come back.
a kind of genetics, and I can't think of the name right now. Epigenetics.
Yeah.
It's exactly
I was
where
gonna say that.
it's changing the, kind of like the biological machinery that's transcribing for the,
Gene
transcribing the
expression.
DNA.
Yes, so
So,
affecting
and that's
gene
passed down
expression.
in the
Yes.
cells. So if you can, I'm not explaining it well.
No, you.
But,
So can I rephrase? So epigenetics is the study of, so genetics is just the study of the information that's in your genome. Epigenetics is the study of how that information is transcribed and used by the cell. And epigenetics can be affected by a lot of things, and it basically has to do with the same way that pretty much everybody has the same gene for melanin in your skin and in your hair pigmentation, but different people have different epigenetics that cause that to be either transcribed more frequently, leading to darker skin and hair, or less frequently, leading to lighter skin and hair. And so the epigenetics is basically how often something gets used in the genetic code. And so that can be affected by things like diet and drugs and things like that, and passed down, where they're still working on figuring out whether it's passed down or not. What were you gonna say?
Like diet, exercise,
Yeah,
things like that, but it's not like hardwired.
it's not as
It's the
hardwired.
software, it's not the hardware.
Yeah, and we think it can be passed on genetic or to your offspring
be
in
passed
some
And
amounts.
that's like Lamarckism too. Like, that a little bit.
I'm not sure I've heard that specific term, but I'll have you explain it to me at break.
Giraffe guy.
Yeah, the giraffe.
Oh, okay. I'll look.
Remember it?
I vaguely recall that. Yeah.
So the giraffe
Yeah.
stretches its neck to get to the next.
Yeah. Okay. Yeah. So there's definitely some aspect of that can be passed on.
And so,
It's not quite genetically, but it can be passed on to
and
offspring.
it's incredibly hard to like determine or measure.
Really hard to quantify. We still don't know enough about it, and there's still so many variables that go into the epigenetics just of a single cell, let alone a whole person. And whether or not those get passed on, or whether or not your reproductive system cells are communicating with your muscle cells that are used to all this exercise, and how much interplay there is still a subject of research right now. So it's hard to say entirely, but we do know that there's a pretty good likelihood that the magic mushrooms affect society formation, but less so about our genetics. It is still a field that's very, very physical anthropology and genetic anthropology is still a field that's still developing. So it's possible that I could be totally wrong about that, and we'll find out in a year or something. And you are free to come back at any point and tell me you told me this and you were wrong, and I will say I was wrong. This one's fun because time travel is always interesting, right?
Yeah.
And time travel is interesting because time is basically a fourth dimension, and a lot of people have heard that before. Let me say this, and then we'll go to your contribution. We're not necessarily taking something that didn't exist in another time and adding it in another time, so much as we're moving something that exists currently and moving it back there. So we're changing the state of matter. We're relocating it on the fourth dimension, which is effectively time, but we're not really breaking conservation of mass and energy. Although Stephen Hawking did he has a response to something similar to this, which is essentially that there would need to be enough curvature of space-time to allow essentially a wormhole to open from the future to the past, to allow for people or beings that perceive time the way we do, and not every being in the universe would necessarily perceive time the same way humans do. Arrival is a really good movie that deals with that to some extent, and Slaughterhouse-Five, for that matter. But basically, anytime a time machine was invented and first used, you could never go back in time before that first happened. Because at some point, when you cause enough curvature to create that first wormhole, that's basically creating a hard line where nothing else from the future could ever go back before that time machine was first switched on. Which is really weird, but Stephen Hawking says it, and when he explains it, it kind of makes sense to me. So I trust it for the most part. I trust that he's done the math on that, and we're all talking about time machines in general. This is a hugely hypothetical situation, so I think I trust Stephen Hawking's opinion more than most people.
Hypothetical.
It is a fun hypothetical. What were you gonna add, Jordan?
Okay, so you might not be able to travel back in time, but you can technically travel forward if you slow the rate that time passes for you. Basically, park yourself near an object with enough gravitational pull without dying, and you just wait a bit and leave. Time will have passed slower for you than the outside.
Correct, and that's part of what relativity has to do with time dilation. And the closer you are moving to the speed of light relative to something else, the slower time will be going for you than for whatever you are talking about or using as your frame of reference.
Yeah, true.
And so Interstellar did that pretty well. They did all the math properly on that. If you watch the movie Interstellar, I love that movie. It actually gets almost all the science right. Until they go into a black hole, and then we don't know what happens. So that kind of gives Christopher Nolan free reign to do whatever he wants.
Remember Gravity Equals Love?
More or less.
Yes.
Yeah. That was the meme version of the ending. So this next question, I want to move on to the next one. We can talk about time travel at break, and then.
I was going to talk about the Fermi Paradox.
Okay, so let me explain it first.
Yeah, explain it.
So, there's the fact that we haven't come into contact with another life form scare scientists. that we've been putting out these signals for hundreds of years, and we haven't heard or picked up a signal from anything else. This is what's called the Fermi Paradox, after Enrico Fermi, who worked on the Manhattan Project. He's one of our Nobel Prize winners from that picture of Solvay. He basically, the story about how this happened was basically he was sitting at lunch with a bunch of quantum physicists, and they were discussing their work, and he's just sitting by himself, and then he just kind of yells out, "Where is everybody?" Because he'd been in his head running through these numbers like, well, if there's this many stars in the universe, and every star has this many planets on average, and every planet has this chance of developing life, and kind of getting a really broad estimate in his head, like there should be like 100 spacefaring civilizations in the universe right now. Where is everybody? And so it's based a lot on a lot of assumptions that are kind of outlined here. There are billions of stars with a high probability. Some of these stars have Earth-like planets in the habitable zone. We've actually proven that to be the case by looking at exoplanets. We've found exoplanets that have Earth-like conditions in the habitable region of the stars that they orbit. So we know that there are habitable planets, by our standards habitable anyway, around other stars. Some of these may have developed intelligent life, which turned into civilizations. And some of those civilizations may have developed space travel. And some of those civilizations that developed space travel may have developed technology to travel between stars, or at least communicate between stars using light or radio waves or neutrinos or something like that. But yet we have no evidence that this has ever happened. So the Fermi Paradox is, why not? How come we don't see anything else? And so there's a lot of discussion on both sides of it. One reason could be because they have what are called several great filters, which is, okay, even assuming life develops, which is a big assumption, there's no guarantee that it would ever progress past single-celled organisms. And even if they do progress past single-celled organisms, maybe that's a 1 in a million chance. And then even if they do progress beyond single-celled organisms, they may not ever develop into conscious thought or in anything resembling civilization. Maybe that's another 1 in a million chance. Then of those civilizations, most of them might just die out or kill themselves before they ever develop space travel. Maybe that's another 1 in a million chance. When you start stacking all these probabilities on top of each other, it starts getting less and less likely that any civilization in the Milky Way ever develops an ability to communicate or travel between stars.
Also, space is big.
And space is big.
Yeah.
And time is long, right?
Yes.
It's incomprehensibly long.
Time is incomprehensible. So it's totally possible it's a mass effect sort of situation where there were a prior civilization that was spacefaring and is now extinct, because civilizations do that from time to time. And so it's possible that this has happened, just never at the same time. And we have no way of knowing any of this, because even if we got a signal from something we were convinced was an alien intelligence, we'd still have to figure out what the heck they were saying.
Yeah.
Right? Despite not having a similar numbering system, wavelengths of light that they can see, they might not use language in a way that we do at all. So how do you communicate or decode a message from this other civilization that may have gone extinct millions of years ago, way before their signal ever even reached our planet? Because space is big and light travels fast, but not fast enough. So, there's a lot of debate on both sides of this. There's also what they call the Galactic Predator, which is not related to the movie, which is a shame, yeah. The idea that maybe we shouldn't be putting out these signals broadcasting to the surroundings that we are here, because any spacefaring civilization may have gotten to be the dominant form of life on their planet by being very aggressive and stamping out anything related to them. We would basically be, it would be similar to an unknown continent broadcasting their location to, say, 16th century Europe. That didn't turn out so well for most of those civilizations, right?
No.
So maybe want to be careful about broadcasting that we're here. And maybe that's where everybody is. Maybe everybody else is like, hey, so maybe we don't want anybody else to know we're here. Right? So it gets a little bit,
Yeah, like,
Contact is another really good movie. It's written by Carl Sagan. He was the author as well as being the screenwriter, about if we did get a signal from another alien intelligence, what it might look like and how humans might be able to respond to it.
yeah, like the Galactic Predator theory is similar to like the Dark Forest theory, where each civilization would wipe out every other civilization they encounter because they feared them. The other one is just that the universe is, relatively speaking, young, so we might just be the first intelligent species to develop.
Or they could get along.
They could get along quietly. So it's, as long as we're talking about extraterrestrial life, this
Which is so sweet here from the back.
we should acknowledge that this is an idea that some people have, that alien life is already here and unacknowledged. Seems really unlikely that alien species would go to the trouble of traveling across vast distances between stars to get here and then hide and play pranks like stealing cattle.
Yeah.
Like it seems like I mean, granted, they might not do things that make sense to us. Maybe they think the cattle are the dominant form of life on the planet.
Yeah, yeah.
But at the same time, it seems really unlikely that just in the last 100 years, all of these UFO reports have started to happen almost exclusively in the United States, where people are talking about UFOs, but really nowhere else on the planet. So it seems unlikely that that's the solution to it. Rose and then Mark?
I think it's also been like talked about, like a lot of the abduction stories could also be our like culturally
Exactly.
what is it? Culturally laced or culturally found. Because like a lot of similar stories like about nightmares and stuff happen in other cultures, but they'll talk about like demons and things like that instead of
Demon
aliens.
haunted world.
Bingo. Demon
Also,
haunted
if
world.
we're in the end of Contact movie, I'm just gonna say it. Like, read the book.
Read the book.
They're probably I think they're probably like maybe they're projections of people that we don't understand, or maybe that could be it. Maybe it doesn't have to be extraterrestrial,
It could certainly be something totally not
something
in the physical realm that we're perceiving normally. It is totally possible that aliens have been here and we just called them by a different name before humans knew to use the term UFOs. Again, seems unlikely given the stories, how similar stories are to each other, and the fact that they've been happening for so long and with no sort of resolution or no contact, to use for lack of a better term. It seems unlikely. And Carl Sagan in this book, not in Contact, the book is fantastic, but this book is also about a lot of topics that are what are called pseudoscience, meaning they use scientific terms to spread misinformation or to claim things that aren't exist. So things like the study of Atlantis or ancient aliens, building the pyramids, things like that would normally fall into the pseudoscience
There's no
category.
way ancient humans could be smart enough to build the pyramids.
Well, that's the theory, right? But he actually goes into cultural understandings of like, oh, well, Celtic cultures had these ideas, these similar reports of similar experiences, but it was little green men that were leprechauns, not aliens. But they described the shape very differently. So they occupied a similar space culturally to what we use alien abductions, except it was the leprechauns that looked very different that were coming in and taking people at night. So it's likely that there's a psychological effect. There's something about our psychology or our brain chemistry that causes that to be a repetitive experience, or an experience that's repeated in pretty much every culture on Earth.
Yeah, some scientists have said that maybe alien abduction stories are results of sleep paralysis.
Sleep paralysis, exactly, yeah. So, Demon Haunted World, very good book. You can get a PDF of it for free if you look around on the internet, or used copies, pretty cheap as well. Relevant questions. In the last ICA, you were given atomic mass of helium and then 24 and 26 and asked to solve for 25, right? Everybody remember that question?
Yeah.
Why did we even need to use the atomic are the relative abundances instead of just dividing everything by three in solving for it.
Weighted average.
Weighted average, but why? What is it? What are you assuming if you try to do this? You try to treat it like a regular average.
It's the same amount of all three of them.
That every isotope has the same probability of showing up. If that's not the case, then you can't just divide by 3. That's assuming each of these is just as likely. So what we had to do instead is use the percent abundances, because that takes the probability into account. That every atom you grab at random is not a 1 in 3 chance of being these different isotopes. It's a 78% chance that it's magnesium-24. Right, so the math gets more complicated just because the world is not as simple as there are only 3 choices and you have equal probability for all of them. Are orbitals actually going in circular motion in nature, or do we just use that image? Hopefully this week's lab or ICA helped with that a little bit. They're a circular shape that described where an electron might be found. But the electron is not actually orbiting like a satellite around a planet. That was their first understanding, which is where the term orbital comes from. But really what they're really doing is it's that cloud of where you are likely to find it, and it's somewhere in there. So we treat electrons as though they are waves that have that circular or figure 8 shape. Because really we just know that they're somewhere in that space. Right, so but they're not, so they are actually, that's the right shape that we're looking at, but we can't think of it as being a solid object or something going in that shape around a nucleus in a predictable way. All right, just the same way that when you've looked at the guitar string is vibrating up and down, it's somewhere in between there at any given point. But when we're going to treat it like it's all of those spots equally, basically, because of the uncertainty principle. Are man-made atoms more unstable than the ones found in nature? Yes. This is kind of a, not a segue, but a way to talk about a related concept. Man-made atoms are more unstable than the ones found in nature because if we made an atom that was stable, it would already be found in nature. So by definition, if it's not found in nature and we make it, it's almost certainly going to be less stable, because if it was stable, it'd already be there. Right? So we can make carbon-12 in a lab by going through fusion reactions, and it's just as stable when we make lab-grade carbon-12 as stuff we find in nature. So with that respect, this question is, it's man-made isotopes can be just as stable as ones in nature, but the ones that are only man-made are always going to be less stable because
They don't appear in nature.
they don't appear in nature. They would already be there if they were stable. So this also relates to a discussion about the nature of the universe and how rules, or why conscious life has evolved or not evolved. It's related to, it's called the Anthropological principle, I believe, which is the idea that we can postulate about multiverses and what other universes might look like, but we can't use that to make an argument like, well, the universe had to be designed because the odds are incredibly against our favor for life to develop if the universe wasn't fine-tuned. But on the other hand, we're already here. We already won that lottery. So you can't say that, well, the odds against us winning the lottery were so stacked, therefore there must have been divine intervention, when we've already won the lottery. That's already occurred in the past. And so the fact that we're here even asking about it means that those conditions were already met. So probability doesn't really come into play, because a probability after an event has happened is 1. It already happened, right?
Yeah, and on a long enough time scale, probability always ends up
And a
being
long
1.
enough time scale, probability always goes to 1. Everything will happen eventually.
Yeah.
Which also relates to Interstellar. Their description of Murphy's Law in Interstellar is a fantastic way to think about chemistry. Not everything that can go wrong will go wrong, everything that can happen does happen. Chemistry is like that. Everything that can happen does happen in chemistry because we're dealing with such large numbers of atoms and molecules. There's a statistical chance that something happens, it will happen. Maybe not often, it might take a while, but it will happen eventually. And then one last question about, this is at the end because it's not all that relevant. Lewis of Lewis dot structures never won a Nobel Prize, but he was roommates for most of his life with a man named Langmuir, who did win a Nobel Prize. Lewis was nominated something like 41 times for a Nobel Prize and never won it. Had mental health issues for most of his life, and the last day of his life, he went out to lunch with his old roommate who just won a Nobel Prize, went and played a game of bridge with some of his colleagues, and then went to work in the lab and was found with a capsule of hydrogen cyanide gas broken, and he was found dead. So the question is, was that an accident or was that suicide? The reason this is worth discussing, we're never going to know for sure. The coroner's report said there was no damage due to hydrogen cyanide, but in the early 1900s, it was pretty common for coroners to cover up evidence of suicide just because it was social stigma, right? So we will probably never really know, but is one example of a pretty high rate of suicide among theoretical chemists and physicists. And no, it's gets put in a little bit of a jokey way here. It's not a joke, clearly, but this is a real story. Ludwig Boltzmann, that we'll learn about when we talk about entropy, developed statistical mechanics and died of suicide in 1906. His prize student, Paul Ehrenfest, died similarly by his own hand in 1933. This is from the preface to a statistical thermodynamics textbook. Wow. The first paragraph. Now it's our turn to study statistical mechanics. Perhaps we should do so cautiously.
That's from a freaking textbook?
It's from a textbook called States of Matter.
Oh my god.
It's making light of the situation a little bit, but it's a lot like a lot of early 1900s authors as well. You know, Hemingway killed himself. There's a huge number of male authors from the early 1900s and male. There's some suicide in female circles at that stage, but it's a lot less common in the sciences, probably because there are fewer women in the sciences, although now that I think about it. So it's definitely something that not to say that studying chemistry will cause you to commit suicide, but it's a topic of raising awareness. And I hope I didn't offend anybody by using a sort of jokey example, because it's a very serious thing. And nobody knows exactly why it is, other than this is the history of it and how things have happened in the past. Mark, and then Jordan?
I was going to say, a lot of bad stuff was happening at that time.
Yes, there was a lot of bad stuff. Everybody was gearing up for World War I, that they were pretty sure was going to happen. It was just a matter of time. There was a lot of change happening. A lot of heavy metal poisoning was pretty common at that time, which manifests as mental illness sometimes. So there's a lot of reasons why that could play a role in this.
Science was the best place at that time.
Yeah, and science was a lot of times people got put in science because they didn't fit in anywhere else. And so you had a higher than normal instance of people who couldn't hack it in the real world getting put into the sciences because they can just spend their time in their lab and do what they want. And it's no big deal. So there's also that if you were rich and white and male and you didn't know what to do with your life, they were probably going to pressure you to study science. And some of those people wound up committing suicide, clearly. Jordan?
Okay, so first, Henry, he's the guy who thought the FBI was spying on him, right?
Hemingway?
Yeah.
They probably were. He spent a lot of time in Cuba.
Yeah, that's awesome. But also apparently when his children asked to see the file on him, all the FBI had were letters sent in by Hemingway by him. And second, referring to the heavy metal poisoning, do you guys know where the phrase "mad as a hatter" comes from? It comes from the heavy metal poisoning because they use mercury a lot in that industry.
Correct. They wet the brims of hats in 1800s in London with mercury to help them keep their shape the way we use starch on shirts now. And they would just stick their fingers into mercury, rub it along the brims, and then lick their fingers to clean them off before going on to make their next hat. And so that is where the Mad Hatter from Lewis Carroll comes in, because the expression was mad as a hatter. Because it was, they used the quicksilver to shape the brims of the hats.
Exactly. How do people not realize that mercury was literally poisoning them for hundreds of years?
I mean,
Because it took decades and before any sort of outward signs were manifested.
Doesn't mercury burn your skin?
No. It's not so bad. I played something with it when I was a kid.
Oh, I see.
They used to give it to kids in the 60s to play with. It was like, here, check this out. This is cool. Like the same way that you give people Play-Doh.
Liquid
Yeah.
metal.
Yeah.
Giving people gallium now.
I'm not that old, but I had a toy that had liquid mercury in it, and I remember breaking it open and playing with it.
Gasoline.
Yeah, that's what that was gas.
Oh god.
So, heavy metals. This is relevant very tangentially, because heavy metals do show up in the periodic table. We're talking about orbitals and the and in general how orbitals affect properties today. And I wanted to show you, this is what's called the wide form periodic table. Remember how I mentioned how the F block should be in between the S block and the D block?
That looks so much more legit.
It is so much more legit. The problem is it doesn't print legibly on a sheet of 8.5 by 11 paper.
Legal paper.
You could use legal paper. We could just get longer printers. We could get printers that print off of a roll. But for whatever reason, the F block is commonly just removed and placed below so that it has better, not aesthetics, but better printing capabilities. But really, the F block does belong right here. And so this is one example of a alternative periodic table, alternative to the form that we are commonly using these days. And this is a better version. It's not the only other version. This is better in the fact that you don't have to remember, oh wait, hey, the F block goes in there. Most of you got the electron configuration of mercury right, and this might have helped you if you were looking at it this way. If you remember that your D block is offset by one spot, one row, your F block is offset by 2 rows, so the first F orbital that you see belongs to n equals 4. But for the most part, most of you did pretty well getting to mercury down here. Writing the complete configuration. Everybody listened to me when I said, write all of them out and don't use the abbreviations. That makes me happy inside. When my students listen, when I tell you how I can give you points. You'd be surprised at how often that doesn't happen. So, good work on that. I'm impressed, frankly. The reason that it has this shape, though, as we talked about in lab this morning or yesterday, because really we have molecular or atomic orbitals that are arranged by energy, and these atomic orbitals are always going to get filled up the same way. They're always getting filled from the bottom up. So if we wanted to practice and look at this, so this is never going to change. When it's empty, this is what they look like. The thing is that you might notice is as you start going up, they start getting a lot closer together. Right, we saw that even with just the Bohr diagram, right? When we had n equals 1, and then n equals 2, and then equals 3, and then equals 4, and then equals 5, 6, 7. They start getting asymptotically closer together. As you get higher and higher in energy, these orbitals getting closer and closer together means that there are some irregularities with how they fill up, especially in the D and the F block. Because the D and the F blocks have so many electrons in them, there are other things that can happen as we're putting in more electrons here that mean that they don't fill up quite as predictably as the S and the Ps. And we'll talk about how that works in a minute. For now, let's practice by just going for zinc. Number 30, when it's neutral.
1s, 2,
So the electron, yeah, so if we're filling this in, we would just be drawing it and filling in the arrows. But the shorthand version would be
Already got, no, wait.
1s2, sorry, I didn't mean the shorthand like that, I meant drawing the electron configuration, writing it out.
2s2.
2s2, now we're right here,
2p6,
2p6,
3s2,
3s2,
3p6,
now we're right here, 3p6,
4s2,
4s2,
3d10. You said zinc, right?
yeah, 3d10. And now we're back, if we count up all these electrons, we've got 30 electrons in there. That gets us to the end of the first d orbital.
You said technically, when you write that though, you can also do 3d10, 4s2.
It would not be wrong to switch these two. Some textbooks write it this way. 3d10, 4s2. I prefer to write it in the way that follows this, because
Which
that
way
makes
they-
the most sense to me.
Which way they fill up?
Which way they fill up, yeah.
Yeah.
Writing it this way is going to usually be more accurate if you're talking about which ones are you going to lose first, are going to be the ones at the end. Right, but different textbooks write them differently, so I'm not going to be picky. Both of these would be considered right for this class. If we wanted to fill in the appropriate number of electrons, we would make sure we did one spin up and spin down. For each of these, up, 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 down, 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 up, down. Not like that. There's our 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total of 30 electrons there. So this would be the atomic orbital diagram. This would be the electron configuration. Related, one will give you the other. But they're showing things. This is more like the more accurate zoomed in version. All right, so a quick definition. We've already talked about this in lab, but just to reiterate, how many valence electrons does zinc have right now?
2.
Zinc has 2, 3, or it's only 4.
So the valence energy level is N equals 4. Or so, and a lot of times you just see it abbreviated as the valence shell, or N equals 4. If we want to know how many valence electrons it has, we would just count up all the electrons in N equals 4. Basically, anything with 4 in front of it is in the valence shell. That's why we label them like this. So zinc only has
4 valence.
2.
Sorry, I saw it.
I have a question.
Mm-hmm.
So if this 3D orbital wasn't filled up all the way, would it still, you would go up to 4?
Correct. So pretty much everything in the D block, as you're adding more electrons, you're adding them into the D orbital that's one energy level down, right? So pretty much everything in here is going to have 2 valence electrons, because only the 2 electrons over here are in the valence shell. And as you're adding up to 10 electrons here, that's going into N equals 3, not N equals 4.
And then does the 4S shell, is it bigger than the 3D shell?
It
And
is.
that's why?
It's larger than the 3D, but the reason why we fill it up first is because it's lower in energy. It's lower than energy. The 4S is lower than energy than 3D until we fill the 3D. Once you fill a d orbital, it becomes so stable that you're never going to break it up again. And all of a sudden, it kind of like settles down a level or two in terms of the energy. Physically, it doesn't move, but energetically, it becomes lower in energy. So if you're going to take something away, it's going to come from the 4S.
So if you have your 4S filled up and your 3D is partially filled, those 3d orbital ones won't interact with anything?
So I'm glad you brought that up. So for starters, if we wanted to, I believe the next question was going to say, well, what happens if we lose those valence electrons? We talked about this a little bit. It's going to come from here, because once you fill up a large orbital, a p orbital or a d orbital or an f orbital, once it's filled, you're never going to break it up again. It's so stable, because orbitals that are filled are way more stable than orbitals that are partly filled. So if our choices are, we can either empty the s orbital here, or we can take 2 electrons away there, and now we have a partially filled d orbital. We go from all the way filled to partially filled. This is way less stable than it was. So instead of breaking up a d orbital, we just take it away from the s.
That's only if it's full.
Only if it's
So
full.
it's like, let's just say the element that we had wasn't a full 3D orbital, would we just take the 2 away from the 3D and leave the 4s full? If we
That's-
already had them missing?
That's exactly. So and it doesn't. It's not as predictable as that. Is part of the problem. Reason my head hesitated.
Mhm.
It's because there are other things that can happen in here as you're filling this up. When it's partially filled. So for instance, we looked at iron. Iron is right here.
Yeah.
So it's got 6 electrons in the d orbital, and it's got full 4s.
Mhm.
So we're looking at something that looks like this.
Right.
You can take away these 4s electrons, but the most stable state is when, if you can't have an orbital that's all the way full or all the way empty, the next best option is exactly halfway full.
So you take away a D and an S? Like
So you would take both of these away and take one of these away. So a lot of these transition metals, a lot of the metals in the D block, in the middle of the D block especially, have multiple possible stable ions. Because you could leave the d orbital alone and just take these away, and that would give you iron with a 2+, which is somewhat stable. But if you take away the third one, now you get iron 3+, which is even more stable.
What did you call them? Multiple stable what?
Multiple stable ions. I mean, ion is just anything that has a charge. So for these transition metals in the D block, most of them have more than one possible stable charge. Copper can be +1 or it can be +2. Mercury can be +1 or it can be +2. Chromium, no, manganese has 5 different stable ions. It can be +2, +3, +4, +5. No, not +5, +6 or +7. And each of those is going to have its own electron configuration that is stable enough to exist long enough for us to measure it. Maybe it's not the most stable state. Maybe if you let that continue being oxidized, let other things steal its electrons some more, it'll settle down into its most stable state. Iron with the 3+ charge is the iron that we're used to thinking of as iron rust, that reddish color, iron oxide. Iron 2 is actually yellow. Iron 2 oxide is yellow. If you take that and you expose it to more oxygen, it turns into iron with a 3+, because that's even more stable. So a lot of these in the D block, especially, are going to be a little bit tricky to predict what their stable charges are going to be, because the d orbital does weird stuff.
Was half of the D orbital, on average, more stable than a full S orbital? Or no? Is that depending on the element?
Depends on the situation, because these things are so close in energy to each other, and every time you add another electron in here, it's going to shift these up and down just a little bit. And so when you get to certain configurations, it actually is easier to add another electron here instead and take it from here, basically. So I'm not going to have you memorize all of the possibilities. And the detailed periodic table actually has the common charges for all of these listed underneath. At the very last thing on here are the charges that you're most likely going to see it in. So for nickel, it's +2 and +3. +3 is bolded because that's more stable, more common than the +2 form. but we are going to be able to relate that back to these orbitals and electron configurations with those few most important rules. Full or empty is the most stable. And if you can't have full or empty, half full, exactly halfway full, is the next best thing. Zeke?
Applying all that to Lewis dot structures, can we just do the Lewis dot structure of iron real quick, just to look at that? Because you said it's the valence electrons.
Sure, actually, let's just look
go to
at zinc, since we have the electron configuration still there.
yeah. That works.
So essentially, Lewis dot structures are not all that helpful for metal ions.
Yeah, I guess my question is more: can we see a Lewis dot structure that is not showing us unpaired electrons?
So zinc looks like this. If we do a Lewis dot structure for zinc when it's neutral, we only have 2 valence electrons, right? So it would look like that.
Right.
If we take away its 2 valence electrons, now all of a sudden the highest occupied energy level is n equals 3, right? That has 18 electrons in it. Because this d orbital belongs to n equals 3. So you've got 3s, the 3p, and the 3d all filled. That's a lot of dots. So we wouldn't do a Lewis dot structure for something that has more than 8 electrons. We basically only use the Lewis dot structure for things that have got somewhere between 0 and 8 valence electrons.
So for iron, when the 3D isn't completely full, you still have your 4s, you've got your 2 valence electrons and unpaired electrons. So I guess.
So in this case, we basically wouldn't do a Lewis dot structure for this one.
Right.
Other than if you were asked to on a worksheet or on a test, if it's the neutral iron, you would just do it with 2 valence electrons. And ignore that partially filled d orbital because it's not the valence shell.
Yeah.
Once you lose those to make it the iron ion, now we've got like 16 valence electrons now, and things get weird. So we would basically never do a Lewis dot structure for that because Lewis dot structures are really most useful when we're talking about covalent compounds. And that happens when you have a bunch of non-metals reacting with each other to make compounds. Metals just turn into ions, and ions just match up with opposite charge to make compounds. You don't make bonds really until you get Lewis dot structures are most useful. All right, one last thing before we take a break. Just one more alternative view of the periodic table is if you really wanted to make a periodic table that mirrored the electronic properties. This version of the periodic table is built around mirroring the properties we can measure in a lab, not quantum properties. If we wanted a periodic table that mirrored the electronic properties, it might be shaped something more like this, where you had your blocks arranged vertically and according to filling from the bottom up. So something that looked more like this, where n equals 1 is the red at the bottom, and that's your hydrogen and your helium, lithium, beryllium. And so this is a valid periodic table. It's just not a common way of doing it. It's useful for seeing how electron configurations work. But it's not commonly used in a lab, mostly because, well, I made this one and nobody knows it exists, but also because there are other versions that are similar to this. They don't get commonly used because you want something that everybody can recognize and know how to use that also conveys as many properties as possible. This conveys just electronic properties and atomic mass. This conveys a lot of things about how things react, as well as what they're, whether they're liquid or gas or solid, or what charges they're likely to have at any given time, which is harder to pull out from a version like this.
Well, just flip your y-axis, and then you got that.
You get something similar. So they call that a left. For whatever reason, they also usually put hydrogen and helium over here in that version, and then expand it to the left. They call it a left step Janet periodic table.
understand you.
There are literally thousands of different ways of arranging the periodic table. And first assignment after midterm is going to be to find some of them and dissect them and kind of see what works and doesn't, including some that are just fun to look at. All right, so we'll take a break here. Let's say come back at, I'm making a short break so we can go, we got a lot of stuff to go through today. So let's go at 10 after. Only 8 minutes, but I'll try to make that up to you.
Today.
Which one?
The one I just started today.
Yes.
I totally answered a couple of questions wrong.
Yeah, no worries. There you are.
So,
Make sure that's not two people's. That's yours, right? Okay.
it's these two that I think I need to just wait until you explain better to answer this, because it's not, that's incorrect.
No, I wouldn't say that. I'd maybe not say valence electrons, but you could say because the highest energy electrons
Right, that's, okay.
are in this orbital. That might be a better way, rather than valence, because that specifically means highest energy level,
Right.
not just highest energy. Energy level specifically is talking about the colors here,
Right.
but energy itself is talking about this version.
This version, so like, for instance, zinc, the valence electron is that, but it's in the D block.
Correct.
So that would not be correct.
Correct.
With the valence electron.
Right, because the highest energy electrons are in the S block or the D block. Yeah.
D block.
Yeah.
Okay, yeah, thank you. You're welcome. Wait, this was wrong. No. You're good, you're good.